Hi, my name is Ping He. I am the co-founder of Labforinvention. We are a 4-year-old company based in Silicon Valley, California, and our team leverages combined expertise from the low-emissivity glass industry, the semiconductor industry, and display manufacturing to develop new technologies for the energy-saving Windows market. Today, we're excited to present our latest invention, a 5G cell phone signal penetrating low-E technology that solves a fundamental problem with low-E Windows. I would like to go over the problem, our solution, and present key performance results based on our lab demonstrated prototype. And without further ado, I'll start the presentation. Globally, low emissivity Windows is a big market. Global sales is estimated north of $40 billion annually, and this is projected to grow at a healthy pace in the coming years due to a combination of climate change and sustainability concerns and related regulatory and policy support from around the world. Low-E windows are great thermal insulators by keeping out solar heat and harmful UV light. But by the same token, they also block out or severely attenuates wireless signal from getting into the building. This results in weak in-building signals. This has remained a challenge for low-E windows for decades. Signal attenuation from low-E windows is severe and is typically in the range of 30 decibels to start for single silver low-E. In cell phone bar talks, this means that attenuation can drop a full mobile reception by 2 to 4 bars, and attenuation will be worse for double and triple silver low-E products. In other words, the problem is severe. Currently, the prevailing market solution to circumvent low-E signal attenuation is by installing indoor cellular aids, consisting of a combination of routers, antennas, and repeaters that can transmit and enhance wireless signals from outside into the building. Considerations for such cellular aids include costs and technical issues around carrier dependency, privacy, security, and increasingly 5G compatibility. A less common solution is using a laser scriber to cut patterns onto the low-E coating, thereby breaking the Faraday cage to allow cell phone signal to pass through the cut areas where it is electrically non-conductive. Challenges with this method are around manufacturing scalability, costs, visual clarity, and durability, particularly around the cut areas. With the rollout of 5G globally, particularly here in the US and also in Asia and developed regions in Europe, the solutions that currently are used to address low-E signal attenuation become more challenging. For indoor cellular aids, which we just covered, this means additional installs, new installs, equipment upgrades, and related maintenance. For laser scribing, the speed of laser cuts for the size of a pattern that can be created become a challenge. What this means is throughput, particularly at the high band, mid-band, and high band 5G become insufficient. And by high band, here I mean 28 to 39 gigahertz, but can potentially go up to 60 gigahertz and more. With an understanding of the challenges that I just previously laid out, what we have created is a technology that addresses low-E's signal problem by leveraging existing proven lithographic production technology to deposit a proprietary imaging pattern onto the glass substrate in order to enable cell phone signal transmission. Our technology consists of a set of patented structures, materials, and processes to achieve a scalable and cost-competitive solution that ensures adequate production throughput, visual clarity of the glass, and that is 5G compatible, all without compromising low-E's thermal and optical performance specs. Here is a quick look at our current technology portfolio, consisting of a set of provisional and non-provisional patents filed that cover a range of claims, including structures, materials, and processes. Key technology innovations include a solution that enables pattern deposition without etching, a mass manufacturing solution using existing production technology while significantly reducing investment costs associated with traditional lithography-based production, a solution to overcome durability issues typically encountered in laser scribing, and a solution that ensures no pattern lines can be seen by the naked eye at any distance and any angle. And for the next few slides, I would like to give a quick overview of the performance of our lab demonstrated prototype that's been developed in-house, developed and tested in-house. The latest prototype we have developed, we call it Generation 2.5. They are 50 millimeter by 50 millimeter in size, exhibit excellent visual clarity, and can meet low E thermal and durability specs, as well as demonstrate excellent signal transmission at the 5 GHz band. A little bit more detail. On the left side is a Generation 2 prototype that we developed previously versus Generation 2.5 on the right. Key improvements from 2 to 2.5 are 1, a reduction in imaging pattern size. What we're talking about here is on the left, Generation 2, pitch of the grid is 2 millimeters. We've reduced that down to 0.5 millimeter in our Generation 2.5 prototype. And correspondingly, the line width has also been reduced from 10 microns in Generation 2 to 5 microns in Generation 2.5. And all that translates into improved performance when it comes to signal penetration. So the signal attenuation under the Generation 2 prototype is around 5 decibels, tested at a 2.4 gigahertz. That same signal loss becomes 5 decibels at 5 gigahertz under Generation 2.5 prototype. Regarding signal penetration, a little bit more detail. Our lab demonstration has shown that our Generation 2.5 sample results in a 5 decibel signal loss compared to a 27 decibel signal loss for equivalent single silver low E coated glass. This is tested using a 5 gigahertz wireless signal. We're currently developing our Generation 3 prototype to demonstrate signal transmission at the high band 5G band, which is 28 to 39 gigahertz frequency bands, which are the two primary high band 5G spectrums deployed by the major US carriers. In terms of durability, Generation 2.5 exhibits good specs under bake and boiling tests that we performed in-house. And here is a microscope inspection based on the test we ran. And importantly, based on our in-house testing, the current prototype is able to meet the major low E product performance specs in color and visible transmission. Scorecard and spectra are presented on the right for reference. Furthermore, in later generation prototypes, we can optimize the performance to meet a variety of customer needs, as is a standard industry practice. And when it comes to glass products, visual clarity is very important. In contrast to a laser scribe solution, where the cut lines can be seen, our imaging patterns cannot be detected by the naked eyes at any distance or angle. Only under microscope and in special light conditions where you can see very faint lines, we presented a microscope image on the right. For those that are clear, maybe you're able to make out the lines, but they're basically run across where the arrows are. That's it for our presentation. We are very excited by our invention and the impact they could have on the energy-saving Windows market. We hope that one day our technology can be found on every piece of low-E glass, and the world will no longer have a problem with cell phone signal reception. Thank you very much for your time. If you have any questions or would like to learn more about our technology, you can reach myself, Ping, or Guowen at our respective emails shown here. Thank you.